Okay, so today we want to find the volume between these two geometric shapes, and we're going to find the volume enclosed. So this volume in here. So to do that, there's a few ways. We could take a triple integral and convert to polar, or you could just subtract the top function from the bottom function, and then integrate in polar coordinates. So we're going to do the latter because it is much easier, and some of you may not have seen triple integrals yet. So let us start. So what we're going to do first is we're going to observe this and think of a good way to solve it. Well, clearly polar is rather easier because we see it has a very, circular shape to these geometries. So I'm going to convert both of these to polar first. So we're going to get z, oops, let me erase, z is equal to 4 times x squared plus y squared. And we denote here, we're going to do r squared equals x squared plus y squared. And we will sub that in. So 4 equals r squared. Now we'll do it for the second one. So we see that z is equal to 5 minus x squared plus y squared. And we will see that z now equals 5 minus r squared. So now let us take this function and subtract it from this function. And that will give us the difference in the function. So we could do 5 minus r squared. I'm going to do the rest. I'm going to do this one in red from now on, so I have to keep changing the color. Minus 4r squared. This will now give us 5 minus 5r squared. And that's what we're going to be integrating over. So this is what we're going to be taking our integral of. So now let's find the regions of our integration. So we want to find, what are we integrating it to? So we have, we're going to have theta, and we're going to have a radius. And here we go. So, we're going to start at, let's just say this is, I'm not exactly sure which one's x and which one's y, but let's say this is our x. Y didn't change the color. This is our x, and this is our y. So we'll be integrating, clearly all around this in the contact. This is 0, and then we're back at 2 pi. So this is going from 0 to 2 pi. What is our radius going from? Well, we see our radius is starting at this 0, and it's going to keep increasing up until this point. So our radius is going to go from 0 to this r. And we can solve it by setting these functions equal to each other. So let's do this. Let's say that we'll use the r polar one. So we're going to say 4r squared is equal to 5 minus r squared. So we're going to add r squared to both sides. We're going to have 5r squared equals 5. And then we're going to r squared equals 1. We're going to r equals plus or minus 1. But radius can never be negative, so we're going to get it's 1. And so why can't radius be negative? That's always a great question. Well, think about it. You never have a radius pointing in a negative direction. So our rotates with theta. So if you want to describe a negative x, you could say, well, pi times r, right? That'll give you a negative x, or x equals r cosine of theta. Let's say r equals 1 and cosine equals negative pi, you get negative 1x. But r is still positive. R is a function of theta to give you a x value. So that's why r can never be negative. So we get now we're going from 0 to 1. So now we can set up our integral and take it. So we know that we're going to get the integral from 0 to 2 pi. Our integral from 0 to 1 of our function here, 5 minus 5r squared. And since we're using polar, we have to do dr d theta. And this extra r comes from having, so if you take, let's say you have some surface and some polar. You have a differential amount d theta, right? So you have this d theta, this small amount of angle. Let me draw this a little bit bigger. So if you have polar. Oops, that was very strange. So if you take this, your r, your length of r, right? So this is your r, which is right here, and you take a little bit more. I'm going to do this in blue. A little bit of dr here, and then your little bit of d theta, which is going to give you something like this. It's going to give you something like this. You're going to get this small area. You're trying to integrate over that area to get a volume. So that's where really the r d theta comes from. Also comes from the Jacobian, which is very fascinating. We can actually compute a Jacobian, but I'm not going to do that in this video. So now we're just gonna integrate. And another way to set up this integral too that's interesting is if we do from 0 to 2 pi, 0 to 1, z bottom, z top, r d dz, dr, d theta. And this will give us the exact same thing because all this is going to do is you're going to get a z and then you're going to subtract them, giving you this. So that's, maybe an intro to triple integrals for you guys. So we're going to do integral from 0 to 2 pi. Now we're going to integrate it, and we're going to factor the r through because I make mistakes all the time, and I don't want to make a mistake in this video, and I don't like to confuse people. So we're going to get dr d theta. So now we're going to integrate, and we're going to get that the integral from 0 to 2 pi. Well, we see clearly that this function is not ever going to be a function of theta. There's no theta in the blue integral limits. There's no theta inside. So we can just times it by d theta. And then we're going to get our integral here. Well, the integral of 5r is going to be 5 over 2r squared, and then we're going to get minus 5 over 4r cubed, and then our limit's going from 0 to 1. So now we're going to get, well, the integral of d theta is just theta, and then that theta is getting those from 2 pi, so we're going to go, I'm going to move down here, we're down here now. We're going to get theta 0 to 2 pi, and then we're going to get times, we're going to get 5 over 2, 1 squared, minus 5 over 4, 1 cubed, minus, well, you plug in 0, you get 0, minus 0, that goes away. So now we're going to get, well, that's just 2 pi times, this is just 5 over 2 minus 5 over 4. Let's get some common denominators. We're going to get 2 pi. That's going to be, well, times top and bottom by 2. You get 10 over 4 minus 5 over 4. We're then going to get 2 pi times, that's 5 over 4. If we now do it in green, because we're last step, well, we can just bam, bam, that's a 2 now. We're going to get 5 over 2 pi. And that is the volume enclosed by these two surfaces. So I hope you guys really enjoyed that video. If you want to see this part, I'll leave it here for a few seconds. We'll go to the top. Bam, boom, we did it. That's what I'm talking about.